Hey Phys 1 kids, Campbell here. In this video we're going to talk about the law of conservation of energy. Now we've already talked about work and how we can apply a force over a distance and transfer energy into a system. We can lift a book and get gravitational potential energy. We could push on something and give it kinetic energy. Those are energy transfers. But in fact, within a system, we can convert energy from one form to another, and that's called an energy transformation. So within a system, an isolated system, we can have kinetic energy going to gravitational potential energy if I throw a ball up in the air, and then that gravitational potential energy will get converted back into kinetic energy as it falls, and maybe then I'll generate some thermal energy due to air resistance, or it'll hit the ground and I'll generate some thermal energy that way. So there are ways within a system that one form of energy can be transformed into another. And in fact, if the system is isolated, if we're not doing any work on the system, if there's no external forces, then the total energy of a system is constant. That's the law of conservation of energy. In an isolated system, the total energy remains constant. What happens, it's not that it just stays in that form though, it gets interchanged, it gets transformed from one type to another. But beginning and end, initial, final, they have to be the same. Now, an isolated system, remember we talked about this previously, an isolated system is one in which there are no external forces. So there's nothing doing work on the system. Some examples of energy transformations, if I talk about this woman and the barbell, which looks super heavy, she's lifting the barbell above her head, so she's taking chemical energy from her body and converting it to kinetic and gravitational potential energy. Or this diver here, he jumps on the diving board and he generates some elastic potential energy, which then gets converted into kinetic energy as he goes up in the air to gravitational potential energy. And at the very top, he's just got gravitational potential energy, and then he starts to come down, and that gravitational potential energy gets transformed back into kinetic energy. So what is kinetic energy? We've talked about what the types of energy are, but we haven't really gone into detail. So let's do that. Let's get some equations here. So remember, the unit of energy is the joule, and kinetic energy is the energy of motion. But kinetic energy can actually be in two forms. It can be translational for motion along a path. That equation is 1/2 mv squared. The unit, or the symbol we use for kinetic energy, is a K. And we could have rotational kinetic energy. If something's spinning, right, it's moving, so it has kinetic energy, and we call that kinetic energy rotational kinetic energy. We have a different equation for that using our rotational equivalents to mass and to velocity. And so rotational kinetic energy is equal to 1/2 I, the rotational inertia, times omega squared, the angular velocity. So 1/2 mv squared, or 1/2 I omega squared. Or if something is rolling, right, it's rotating and translating, and then we have both. But that's a subject of a later video. Where does this equation come from? Do we just like make this up? Is that what we do? We physicists, we just make stuff up? Well, it actually comes from work. So let's talk about two-man bobsled. Two-man bobsled, right? They're pushing their sled, they're applying a force to move it a distance, and they're giving it kinetic energy. So they're doing work that becomes a change in kinetic energy. Work energy theorem. Well, we can break this into its components, right? Work is force times distance. So the force of the push times the distance equals a change in the kinetic energy of the sled. Well, let's go back to Newton's second law in kinematics. If you remember in Newton's second law, the net force is equal to mass times acceleration. So there's force of push. So the force of push results in the acceleration of the sled, right? Change of velocity. And from kinematics, if we think about changes in velocity and acceleration, in this case we're talking distances. So let's use that, what I call the third kinematic equation. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in x, which we'll call d, since that's what we do when we do work. If I rearrange this to solve for acceleration, so I can put it in here, right, that gives us acceleration is the final velocity squared minus the initial velocity squared, right, just move that over, then divide by my 2d. All right, and I'm going to put that in for my acceleration. So we'll put that in over there, and we get force of push is equal to mass times the quantity V final squared minus V initial squared over 2D. That's a D. Let's distribute the M. So we'll put the M inside here. And let's move the D over here. Right? If we multiply both sides by D, we get force of push times D is equal to mv final squared minus mv initial squared over 2. Oh, holy cow. Wait, force of push times D, so work is equal to 1 half mv final squared minus mv initial squared, right? And that's equal, right, to here, my change in kinetic energy. So look, there's my equation for kinetic energy, 1/2 mv squared. So it comes from work. It's not new. It's just taking what we learned in the previous units on Newton's second law and kinematics and putting it into one simple, easy form. I have a question for you. This might look a little familiar from the last unit. I have a light plastic cart and a heavy plastic cart, both pushed with the same force for a distance of 1 meter. They start at rest, so their initial velocity is 0. After the force is removed, the kinetic energy of the light cart compared to the heavy cart is what? Well, remember that work equals a change in kinetic energy. Work is force times distance. If the force is the same and the distance is the same, then, and they start at rest, so the same initial kinetic energy, all right, then the kinetic energy has to be the same. That doesn't mean the speed is the same. Let's talk about potential energy. What is potential energy? Well, potential energy is stored energy. It's energy that we can store for later use. It's an energy that's due to the interaction between objects. So that means there are forces involved. There are two types of forces. There are conservative forces, and conservative forces are actually, right, conserved means conservation, which means constant, right? Those conservative forces allow us to store energy, and some good examples of those are the force of gravity and spring force. But there are also what are called non-conservative forces. Non-conservative forces, right, they don't allow us to conserve, so we don't store energy with those types of forces. So not all forces allow us to store energy or create potential energy. In fact, a great or not so great non-conservative force is friction, right? Friction generates thermal energy, and it's really hard to hang on to thermal energy. We're going to talk a little later about what thermal energy is and why that's so hard to hold on to. Let's go into more detail about gravitational potential energy. The symbol for gravitational potential energy happens to be a capital U with a sub G, the subscript of G, U sub G. Why, I don't know. That's just what we use. It is the energy due to position. It's a position measured from some height. Now, remember, potential energy comes from an interaction between objects, so a force, and the gravitational potential energy arises due to the interaction between an object and the Earth, so like the book and the Earth. If we're talking about here on Earth, gravitational potential energy. So the thing is, the Earth has to be in the system, must be in the system. For us to talk about gravitational potential energy. Otherwise, we're going to have to talk about the work done by the force of gravity, the work done by that interaction. The equation for gravitational potential energy is mgh, m being the mass of the object, g the acceleration due to gravity, and h being the height above some reference point. Now, where does this equation come from? Well, let's take a look at this thing right here. We have the book being lifted at a constant velocity, or maybe we're talking about the initial state being the book in my hand at some height, and then raising the book up to some other height at rest. Either way, in this case, we have work changing the gravitational potential energy. So work being the force of the hand times the distance it travels equals a change in gravitational potential energy. Well, if this object is moving at constant velocity, right, then the forces have to be equal in magnitude, or even if they're at rest, right? So says that if I'm moving at constant velocity or I'm at rest, the sum of the forces are zero. They have to be balanced. There's no net force, which means that the force of push is equal to the force of gravity, and the equation for force of gravity is mg. So I could change my force of hand here. I call the force of push, force of hand, whatever. I could change that to the force of gravity times d is the change in gravitational potential energy, and force of gravity is mg. And what is d? Well, d is the displacement of the object, how far I've moved or the distance I've moved that object. And so if we talk about it in terms of a height, right, we could talk about it in terms of the final position minus the initial position. That equals a change in gravitational potential energy. Or we could talk about it in terms of a change in y or a height. And that's why we changed this to h, because we can talk about that in terms of a change in position, height. Now, you'll notice that I have the gravitational potential energy equation here, and that equation is for a change in gravitational potential energy. In fact, anytime we're talking about gravitational potential energy, we may say, oh, the gravitational potential energy is mgh, and the height here is 6 meters, so this is my gravitational potential energy. The thing is, it's measured above some 0 point, so it's really about a change in the gravitational potential energy. So what you'll have to do when you solve problems for gravitational potential energy is you're going to have to set up a coordinate system and dictate where is 0 for height. Usually it's the lowest point of the problem, or the ground, right? That would make it 0, right? That would make sense. And then your gravitational potential energy is 0. And so that's why we just talk about it in terms of mgh. But h is really, it's a height, it's a change in position. Now, like I said before, gravity is a conservative force, and so that means it can store energy. But another thing about conservative forces that you should know is that conservative forces are only the difference between the final and initial matter. It doesn't matter how it took me to get there. So in this case, whether I went up stepwise or I took the steep path up, my change in gravitational potential energy is the same no matter what. I could do a little swirly around, right? That would take longer for me to do that, but my change in gravitational potential energy, initial, final, is still the same. So conservative forces, we say, are not path dependent. Another type of potential energy is spring potential energy. We call it elastic potential energy. I call it spring potential energy a lot, but it's technically elastic potential energy. It's symbolized by a U for potential and then S. Sub S. It's an interaction, right? It's a force that occurs between an elastic material like a spring. Now, energy is stored if we compress or stretch a spring, right? Either way, if I apply a force, if I do some work to push that spring, I am storing energy in it, because if I let go, right, it's going to convert to kinetic energy. Now, the equation for spring potential energy, and I'm not going to derive this one because we haven't really talked much about spring forces and Hooke's law. We're going to do that a lot in our next unit, is 1/2 k delta x squared. Now, k is not kinetic energy. I tried to make a lowercase k so you'd see the difference, because I see kids mix that up all the time. This is a constant, and it's the stiffness of a spring. So if we look at springs, like stiff springs, like springs that might be in the suspension of your car, those are stiff springs. So those would have a really high K value. A loose spring, like say a slinky, that would have a very low K value. So K is a constant. It's a constant value for a spring, and it tells you how stiff the spring is. Now, delta X is how much you've compressed or stretched that spring from what we call the equilibrium position. I like to call that position the happy place. So if I take a spring or an elastic material like a rubber band and I just set it down and I don't touch it, it is at its equilibrium position. It's at where it wants to be if nobody's bothering it. That's why I call it its happy place. So the delta X represents how much it's stretched or compressed from where it would be if there was no forces acting on it. And so you kind of see that in the picture here. This is where the spring would be if it was just at rest and nothing was bothering it. And here would be my delta X. If we forced it to compress, or maybe more, then the delta X would increase. So K, spring constant, not kinetic energy, spring constant. Delta X is how much it stretched or compressed from where it would be if nothing was bothering it. The last type of energy I want to talk about is thermal energy. Thermal energy is all of the molecular motion. So it's not part of mechanical energy. Remember, mechanical energy I talked about previously to be energy we can see. You know, kinetic energy, energy of motion, gravitational potential energy, spring potential energy. Those are types of mechanical energy. Thermal energy is not one of those, because thermal energy is all of the kinetic energy of the molecules inside the substance. It's also called internal energy, and if you take a thermodynamics course, you'll learn about internal energy, and it's associated with temperature, because remember, temperature is a measure of the kinetic energy of molecules. So the higher the temperature is, the more kinetic energy they have, so the more thermal energy that they have. One way that thermal energy gets generated is through the work done by friction. Remember, friction is a non-conservative force, and so friction will generate thermal energy, right? You rub your hands together and they get warmer. So when there's friction, that rubbing between the surfaces increases the molecular motion of the molecules inside the surfaces that are rubbing together. That generates thermal energy. Now, the thing with thermal energy is, because it's the molecular motion of molecules, containing it is very difficult, right? Because the molecules will, even if you try to insulate it, the molecules are bouncing off of surfaces and transferring their kinetic energy to other molecules. So we say that friction is a non-conservative force because, remember, it doesn't store energy, and it's because it's generating this thermal energy that's going to just diffuse out into the environment, because these molecules are just constantly moving. But the other reason why it's called a non-conservative force, another property of a non-conservative force, is that the amount of energy it generates is path dependent, right? The more rubbing there is, the longer this path of rubbing is, the more thermal energy we generate. So non-conservative forces do not store energy, and the amount of energy that's generated or transferred out of the system is path dependent. So the more rubbing there is, the more that path is, the more energy that's generated. Whereas conservative forces store energy, but only differences, final minus initial, are significant, so they're path independent. This brings us to the very last thing that I want to mention in this video, is that work equals a change in energy. So we can create this generalized work energy principle using the law of conservation of energy and this work energy transfer. So what the generalized work energy principle is that the sum of all of the energies initial plus the work done is equal to all the energies final. So whatever I have initial plus how much work is being done by external forces equals total energy final. Now you'll notice the one thing I didn't put initial thermal energy and final thermal energy. I just put it in terms of a change of thermal energy. This is because it's really hard to quantify this. Usually what happens, and you'll see this in an example problem that we do in the next video, that when thermal energy is generated, it's usually a result of the difference we calculated by finding the difference between the initial and final energies. Kinetic and gravitational, etc. So quantitating it is difficult unless we calculate the work done by friction. But again, it's a change. So that's why we would put it in this equation that way. All right, so fill out your WSQ and I will see you in class.